Hi, and welcome back to another LeetCode problem. We're looking at a medium one, and this is LeetCode 46, sort matrix by diagonals. I have not attempted this myself. This is the first time actually looking at it, and I promise you I did not look at any of the solutions. We're going to approach this interview style, trying to focus on communication, analysis, figure out the algorithm before we start coding. And yeah, hopefully that'll work out smoothly for us. So let's see. So we're given an n by n square matrix of integers as a grid, and we should return the matrix such that the diagonals in the bottom left triangle, including the middle triangle, are sorted in non-increasing order. The diagonals in the bottom left triangle. So this is the top right, this is the bottom left. That the diagonals in the bottom, okay, are sorted in non-increasing order. I'm not fully understanding it, but let's see. The diagonals in the top right angle are sorted in non-decreasing order. Okay, non-increasing, non-decreasing. So, okay, 2 and 7, that's increasing. Those numbers are decreasing because it's the middle triangle, 8, 6, 1, 9, 5. So, oh, I see. So we are supposed to sort the numbers along the diagonal. Cool. Let's look at some of the some of the constraints. So it's a square. We're given a square grid or square matrix. We are guaranteed to have at least one element in it. We don't care for the upper bound. Otherwise, our runtime and space complexity analysis is going to be constant. So O of 1, which is of course useless for an asymptotic analysis. And then the cells in the grid are between some value that's negative and positive. Okay. Okay, cool. So how could we approach this? Well, let's look at the examples. Explanation. I think we've already skimmed kind of through that by analyzing this ourselves. The diagonals with the blue arrow, top right angle, should be sorted in non-increasing. So those two. Okay. Example 2, a grid. So 0, 1, 1, 2. When there's only one element, there's nothing to sort. But once we hit the diagonal, we know we need to sort in non-increasing order. So it's decreasing, but not strictly decreasing. Strictly decreasing would be if you don't have consecutive values that are the same. But non-increasing and strictly decreasing is the same thing. Yes. And so, okay, example 3, grid just one cell. So that's the diagonal. There's only one element. There's nothing to do there. Okay, so how could we approach this from an algorithmic point of view? Well, it seems to me that we need to perform sorting. So one thing is we need to try to find a way to get access to these elements in the diagonal in an iterative way. But then we also need to collect these numbers to perform sorting on them. I don't know if it's possible in Python to give a sorting algorithm access to a function that returns the values, because the Python sorting implementation will happen in place, and then we don't need any extra space. Maybe that's something to look up after. But so the first approach would be we just collect these numbers that are on the diagonal, decide if we need to sort them in ascending or descending order, and write them back into the diagonal. So that would be my approach, my first naive approach. Obviously, we have to look at all of the numbers in the grid. And so we'll have an O of n time. And we will have O of n space, square root of n space, because the diagonal here is the longest sequence of digits that we'll have to sort. But since this is a square matrix or square grid, the diagonal has length of the square root of the length of the sides. So I think we can get away with O of n plus the sorting time and O of square root of n base. And so the sorting will be done on x most square root of n numbers. So that will be square root of log of square root of n. Right, that's going to be the runtime. So square root of log of square root, is that less or more than linear? I'm not sure. I don't think I've seen that before. Well, you could probably do some math. I just have to remind myself how this works with the logarithms. If I want to put this into here, I probably have to square what is in the brackets here with that prefix, maybe. Square root of something like that. Anyway, I don't know. I'll probably look that up so that I know for next time. And then, well, how do we pick now the elements that are on, let's say, this diagonal when we want to sort in descending order? Well, we know that all of these start with x equals 0. And when we want to compute the blue diagonals, we know that they start at x equals 1 and the y is always 0. So I think we have two cases here, so we can treat them independently. So maybe we will treat this, the black diagonals first. So 4, well, we should pull out the n. What is our n? N equals length of the grid, because it's a square grid. 4, y in range n, right? 0, 1, 2, and 3. So, and the end of the range is not inclusive. So that's how what we do for the start. Now we need to have well, something for the numbers to put it in, where we want to collect these numbers. Right, and now what we'll do is we will iterate for how many times? I'm not sure yet. So we have to put that in a second. Oh, yeah. Well, we don't actually have to calculate this exactly, right? We can do while y is smaller than n and x is smaller than n. Because if y or x go out of bounds, then we're basically done. So, and we'll start with x0, right? That's what we said. So now what we do is nums.append, and we're going to pick out the number from the grid. And that is, of course, grid at position y, x. So, and y selects the row and x selects the column. And since this is a two-dimensional array, the grid, the first dimension selects the row and the second the column. Right, so that's how we do that. And then we increase our x plus equals 1, y plus equals 1. So when we're here at cell 0, 0, now we want the next one to be 1, 1, etc. So that's what we do. And then we've collected all our nums. So we can do nums.sort. And now we just iterate again and write those numbers back. Right? And yeah. So now what we do is, now since we are so this is now in ascending order, but we want to write them back in decreasing order, which is fine. We just do the following. Very nice. Nums.pop. We pop the last element out and we write it. So that's very easy. And now we will have to deal with the other case. And that is 4x in range 2 to n, right? We start at x at 1, 2. So this is for the blue. And now our y starts at 0. Our nums is, of course, again empty. And we will have the very much the same logic here. Where we just increase along the diagonal. And we append the value that they get from well. Now we sort in reverse order. True. And yeah, and then we do the same thing. And write them back. Now we have to be a little bit careful because we just modified our x value here, right? Inside here. So the writing back doesn't necessarily work like this. Y start equals y. So we have to say y equals y start. And same here. We say x, we remember x start, and now we say x equals x start, and our y equals 0, and we write the stuff back. Now, we have quite a lot of repeating code here, even though this should already be the solution, and then we just, I guess, return the grid at the end. And yeah, return the grid at the end. So what we can do is we can, you know, put this kind of code into a helper function. So let's do that. And how should we call this? Sort there, and we give it a starting value and a y value. And we will, what will we do? Well, we will tell it if reverse is true or false, right? So that we know how we should sort it. And here, what we do is we will remember, oh, actually, we will just do this. X start, y start. Then we just say x, y equals x start, y start. And then the first thing we do is we collect our numbers. And then we sort our numbers. Reverse. And yeah, and we'll make it easier for us, because what we just did earlier was we reversed the numbers, but then it was in ascending order. So we have an off by 1 in binary, so that we need to actually inverse this flag here for the sorting. So that's how we read those values out, and then writing them back is as simple as doing the same thing again, but we're doing now the pop. This. I'm deleting a bunch of code that I'll probably have to add in a second. So, and now we modified the grid in place, right? And what we have to do now, we have to call our diagonal sort diagonal x, y, reverse. Let's see. So if we go by x, then we sort in ascending order. So reverse is false. And we need to iterate over the values of x for x in range 1, length 1 to n. And for y, we do for y in range n. Sort diagonal on the y starting at x0, and that should be it pretty much. I hope I didn't mess it up when I did those changes. Let's check real quick. So we put x and y to our start. We know that we have to increase x and y plus 1 regardless of on which diagonal we are. If we say, so in the case of the blue diagonals, we want to have it in ascending order, so reverse is false. We collect the numbers, we sort them, but we write them back in reverse order. Well, that doesn't work. So that actually won't work. What we would have to do is we would have to start from here to write them back. And but we can't do that. So we actually need an iterator. So while or for I in range length nums, because nums now contains all the values that we have to write. Okay, just do like this in nums. And we'll just add I to y and to x. Yes, that's how we have to do this. So we actually write them from the beginning to top. So this is in ascending order, and the other ones are in descending order. So that is that. And instead of starting from x, y, we start from start x and y start. Yeah. I think that fixes that. Let's just run the tests. Aha, typo. I was too hasty. I should have checked it. Interesting. Cannot access local variable n. Oh, that's because n is defined outside here. We just make this a non-local, and we should be able to access that. Index out of range. Y is smaller than n and x is smaller than n. So in theory, we should be able to access these elements, right? So what is the problem here? Is it because we use n here again? I'm not sure. I don't know Python well enough to do that. But that could be the case. Just make it implicit from 0. We could also, instead of doing that, we could also just pass in the n here if we wanted to. Right? The size of the grid. But we shouldn't have to. So this is a non-local n. Just make sure we're not modifying n anywhere. If y is smaller than n, that should always work. Let me just check one more time. Yeah, the length and the height are the same. So they're always smaller than that. Yes. I think, I mean, it should be okay. Why wouldn't it? Because we checked if they're in bounds. Okay, but we're getting back the wrong result. Are we sorting? Oh yeah, well, we have to flip our flags, don't we? Actually, we do this by flipping this. Reverse is reverse. All right, that looks better. So in an interview, you want to avoid these kind of situations where you have typos, even though that's not a big thing, but you kind of want to avoid having to look at what was the error. And when you're a little bit more focused, you know, you should spot these things as well. So restructuring the code always has a little bit of danger. But yeah, it makes it a little nicer now. So let's submit it to see if it passes all of the test cases. Right, and it seems to work just fine. I don't get this new layout though. All right, so yeah. So now let's see what other people's solutions are. Maybe they have a good analysis for their runtime. Yeah, people always skip that. So that's an interesting one. Dot matrix diagonals, left edge. What is this person doing? Treat each diagonal independently. Time complexity 2 to the n to the power of 2 log n. But why? Let's see what that code does. Okay, that could be 1 because we know n number of rows and columns is the same. So it's creating a result grid. Okay, but then the space complexity is n squared. Oh, time complexity is n squared times log n. So this person is assuming that it needs to sort n elements on the diagonal. So this is why this is a worse upper bound than what we have. Otherwise it would be the same, right? It's n. Oh yeah, it's n times, not n plus. It's n times. Okay, that's one mistake that I made. Yes, but this person doesn't have a tight upper bound. Yes, we have, right? Okay. People never do really a lot of simplest method, just sorting n squared log n. It's not n squared. Space complexity, okay, that's also too large. That should be square root of n should be space complexity because we're only holding the diagonal in memory at any given point in time. Maybe we should share our solution, right? Yeah, why not? Let's do that. I've never actually done that. Oh, Jesus Christ, now I have to do that. Okay, intuition. sort every diagonal independently from each other. Approach, well, for all diagonals and sort them using skirt and space in skirt and log n time. Complexity of n times squared log squared of n. Right. Wait a second. Yeah, well, we have square root of n diagonals, right? Not just n. So we still have n time for visiting every element, but then we only have square root of n diagonals. Squared. I like how this keeps changing. Let's say squared. Okay. Since the longest diagonal is square root of n elements long. There's complexity of n square root of n. Time complexity is, and we have square root of n diagonals. And that means that square root of n times square root of n equals n, right? So this is O of n plus, well, n log square root of n is pretty much it. So n log square root of n time. Yeah. Nice. So that actually became better than before. And if we made a mistake, I'm sure that some smarty pants will correct us. And I guess we have to correct our code first. Okay, may I share a solution. Time complexity, since the long standard is square root of n elements have square root of n times sorting is the number of times we need to sort. Wait a second. Since the longest diagonal is square root of n elements long and we have square root of n diagonals, we will have that log square root of n. N square root of n is okay. Cool. I think that should be it. Can we post that? Why can't we post that tag? Python tag sorting tag array. Yeah, sounds good. Matrix. We don't care about matrix. Do we have to put a title? Okay. O of n log square root of n time and O of square root of n space. Do we put emojis here? I don't know. Should we? Maybe we should. Cool. Let's post that. Yeah, it's always good to try to get feedback, so I will get some feedback. And maybe I'll discuss it in the next video if there is something useful in it. Anyway, thanks for sticking with me for so long. That concludes this little LeetCode problem.